Dear students, welcome you all to this video lecture. This is N. Manikandan, Assistant Professor of Physics from Government College of Engineering, Bodinakino. In this video lecture, I am going to talk about uniform bending, non-uniform bending, and expression for Young's modulus of a beam using uniform bending method. These are the topics belong to the first unit, properties of matter, in the paper Engineering Physics PH8151. Okay, let us move to the topic uniform bending. Uniform bending. What is uniform bending? Suppose we take a beam of length AB and support that beam on two symmetrical knife edges C and D. The center of the beam is E. Now apply a load W on both ends. W on both ends. What happens? The beam bend like this. The center of the beam elevation is produced. This elevation EF equal to Y. This bending is known as uniform bending. Why we call this as uniform bending? Because look here, the bending of beam forms an arc of a circle. That is, this part produce an arc. This part produce a circle. That is, suppose we extend this curve that produce a circle, and in every element of the beam produces the same radius of curvature. Therefore, this is called uniform bending. Now we can easily define what is uniform bending. If a beam is loaded with equal weights on its both ends, bending of the beam forms an arc of a circle. The elevation produced at the center of the beam, this is known as uniform bending. Next, we move to the next topic, non-uniform bending. What is the non-uniform bending? In similar to the previous concept, we take a beam of length AB and support that beam on two symmetrical knife edges. The center of the beam is C. Now apply a load at the midpoint of the beam. What happens? The beam bend like this. At the center, a depression produced. This type of bending is known as non-uniform bending. Why we call this non-uniform bending? Because look here, the bending of beam does not form an arc of a circle, and the radius of curvature is not the same for all elements of the beam. Suppose we increase the load W plus 50, W plus 100, the beam bends like this. This curve not produce a circle. Therefore, this is called non-uniform bending. Now we can easily define What is non-uniform bending? What is non-uniform bending? If a beam is loaded at its midpoints, the bending of the depression produced, the bending of the beam does not form an arc of a circle. This type of bending is known as non-uniform bending. Next, we move to the next topic, expression for Young's modulus of a beam using uniform bending method. Let us consider in similar way from the previous topics. Let's consider the beam AB and supported on two symmetrical knife edges C and D. The distance AC equal to let the distance AC equal to BD equal to A. AC equal to BD equal to A. Center of the beam is E. Center of the beam is E. Due to the applied load W on both ends, the beam bend like this. At midpoint, at the center of the beam, an elevation produced EF equal to Y. EF equal to Y. The distance between the two knife edges equal to CD equal to small l. Here, due to the applied load, the bend is produced. Bending of the beam forms an arc of a circle. This type of bending is known as uniform bending. This type of bending is known as uniform bending. Let us consider the portion AF. It's look like a cantilever problem. Here, at the point we consider AF, here a couple is produced due to the two forces. One of the force is the force acting vertically downward at A. The force W acting vertically downward at A. Another force, the force of reaction, W acting vertically upward at knife edge C. At knife edge C. The two forces, one of the force acting vertically downward at A, another force acting vertically upward at C. A couple is created. Here, the moment of a couple is the product of one of the force and the distance between the two forces. Here, the moment of a couple is the external bending moment. The external bending moment external bending moment equal to W into A. Give equation number 1. Give equation number 1. We know that bending moment of a beam, bending moment of a internal bending moment of a beam, internal bending moment of a beam equal to yi divided by r. Give equation number 2, where y is the Young's modulus of the beam, I is the geometrical moment of inertia, y is equal to Young's modulus of the beam, I equal to geometrical moment of inertia of the beam, geometrical moment of inertia of the beam. R is radius of curvature. This radius of curvature is bending of beam forms an arc of a circle. The radius of curvature of the circle is capital R. Here at equilibrium, external bending moment is equal to external bending moment is equal to internal bending moment. External bending moment is equal to internal bending moment. Now, from equation 1 and 2, WA equal to, we can write WA equal to YA divided by R. Young's modulus Y equal to WAR divided by I. Give equation number 3. Give equation number 3. This is uniform bending method. Here, the value of R, we determine the value of R and substitute this in this equation. We get the expression for Young's modulus of the beam. Now, we use intersecting chord theorem. Intersecting chord theorem. What is intersecting chord theorem? Consider a circle, center O, two chords intersect like this, A, B, C, D. This point F. When the two chords AB and CD, here AB and CD, when the two chords intersect each other inside a circle, the product of their segments are equal. That is, here AF into FB equal to CF into FD. This is a special property of a circle. Now here we use the intersect chord theorem. Here we use the intersect chord theorem. Here, this bend forms a circle like this. In this circle, CD is the distance between two knife edges. L and EF is the elevation produced here. Y. This FG chord and CD chord intersect each other. This FG chord cut the CD at midpoint. Therefore, CE is L by 2 and also ED is L by 2. EF is elevation Y. Here, the distance, what is the distance EG? The whole length FG is diameter of the circle, therefore 2R. 2R minus the elevation value Y gives the distance EG. Therefore, using intersecting chord theorem, we can write CE into ED equal to EF into EG. Here the distance EG is 2R minus Y. Substitute the value L by 2 into L by 2 equal to EF Y into EG 2R minus Y. We simplify this. L squared divided by 4 equal to 2RY minus Y squared. 2RY minus Y squared. Here, compared to the value of R, the Y value is small. If Y value is small, Y squared is very small. For example, if Y is 0.1, Y squared equal to 0.001. When compared to this small value. Therefore, we neglect Y squared. We can write L squared divided by 4 equal to 2RY. Therefore, R equal to L squared divided by 8Y. Give the equation number 4. Now, substitute equation 4 in equation 3. We get capital Y equal to we get W into A into L squared divided by I into 8Y. Equation number 5. This is the expression for Young's modulus of a beam using uniform bending method. Suppose we take rectangular beam, special cases. Suppose we take rectangular beam like this. Breadth B, thickness D. The value of geometrical moment of inertia I equal to BD cube divided by 12. Substitute this equation equation 6 in equation 5. We get capital Y equal to WAL square divided by BD cube divided by 12 into 8Y. We simplify this equation, we get Y equal to 3. 3WAL square divided by 2BD cube Y. Equation 7 is the expression for Young's modulus of a rectangular beam. Suppose we take circular beam of radius r, the geometrical moment of inertia value I equal to pi r power 4 divided by 4. Equation number 8. Substitute this equation number 8 in equation 9. Substitute equation number 8 in substitute this equation 8 in equation number 5. We get capital Y equal to WAL square divided by I into pi r power 4 divided by 4 into 8y. We can write y equal to WAL square divided by 2 pi r power 4y. Here, this is the equation for Young's modulus of a circular beam. In this equation, W equal to mg, where g is the acceleration of gravity, m is the mass, applied mass. G is the acceleration due to gravity. Okay.